So, hi everyone. So our second speaker is Changliang Wang. He is from Tongji University in Shanghai. So his talk title is Singular Matrix with Non-Negative Scalar Curvature and RCD. So Professor Wang, you can get started.
Thank you. So introduction, I thank organizers for invitation so they can talk about some recent work here. Yeah, this talk is based on some joint works with Professor Xianzhe Dai, Professor Lihe Wang, Professor Guofang Wei, and so Dr. Yukai. Yeah. So, right. I think I'll split the talk into two parts basically. So first part mainly focus on the conic singularities, about positive mass theorem, and also non-negative scale curvature with conic singularities. But actually, this is a simple case. It's in Minan's talk. Right? But here, of course, we'll also have positive mass theorem for non-spin setting. Okay, and this part, I think we have talked about that on not only scalar curvature seminar. I think about 1 year, 1 year ago. So this time, but it's very related to the second part. It's about actually mainly about the existing problem of singular metrics, and in particular, we'll get some small extension result for L infinity matrix with non-negative scalar curvature. Right. So this is more. The second part is more recent work. Okay, so now let's start with the classic positive mass theorem. Yeah, this is motivated by the study of general relativity in physics, and it turns out to be a very important, very fundamental result about the studies of scalar curvature in mathematics. So this positive mass theorem, the classical positive mass theorem, is actually a theorem on so-called asymptotically flat manifold, or asymptotic Euclidean manifold is also called. So that is the asymptotic flat manifold is a complete Riemannian manifold, and it contains a compact subset K, and the complement of K consists of finite many collected components we call ends, and each end is diffeomorphic to Rn minus 1. So on each end we have a global coordinate system, and the Euclidean asymptotic flat basically here means this metric on each end is asymptotic to the standard Euclidean metric. It's a Euclidean metric plus some perturbation term as h. H decays as we approach to the infinity. So and this H has some and we also have some restriction requirement for its asymptotic or decay orders. Tau we require greater than half of -2, and also we assume scalar curvature is integrable on the whole manifold. Okay, so for this kind of asymptotic flat end, the three physicists defined mass. This is now called ADM mass. This is a limit of a flux integral of certain combination of first derivative of the metric. So here, so the xg are just asymptotic flat coordinate in the definition. And from this definition of this mass, we see it may depend on the choice of asymptotic flat coordinate system, right? This is not unique, this choice of coordinate system. But under the asymptotic conditions for the asymptotic order of perturbation term H and the integrability assumption for the scalar curvature. But you can prove the mass actually is well defined. It means it only depends on metric G. this geometric invariant of the metric G. Okay, so let's look at two simple examples. First one, the simplest example is Euclidean space. It has one end and the mass is 0 because the metric is constant. And second example, so non-trivial example, the very important example is a Euclidean Schwarzschild manifold. All right. So now this time the manifold is a Rn minus Euclidean origin, and the metric is the conformal deformation of the Euclidean metric. Right. So conformal factor, the main thing here is actually Green's function of Laplace operator on the for the Euclidean metric. So R is the distance function to the from the Euclidean origin, and so this manifold has two AF ends, right? So one is for R goes to infinity, right? This is correspond to the Euclidean infinity, and another is another comes from the Euclidean origin. That's for R going to 0. And so clearly this is scalar flat, right? And the scalar curvature is 0, identically 0 on the manifold. And the mass, ideal mass are for both AFN are 2m's positive. Right? So you get, so here example with 0 scalar curvature and positive mass. So the positive mass theorem, the classical positive mass theorem says for asymptotic flat manifold, if the dimensions between 3 and 7, all the m is spin, then if the scalar curvature is non-negative, then the ADM mass is a non-negative, and the rigidity part says the mass equal to 0 if and only if the manifold is asymmetric to Euclidean space. So it's was first proved by Shenyao using minimal surface method, and then by Waiting using Geroch operator method. And more recently, Shenyao wrote a paper for extending their argument to higher dimensions. Okay, so I think for either method, actually the index theorem is very important ingredient, right? Even for minimal surface method, I think the Gauss-Play formula was used, right? Okay. So I think I would like to mention another approach to the positive mass theorem, so because Shenyao low cap compactification. Right? This is a kind of argument by contradiction. Yeah. So let's say we have asymptotic flat manifold with non-negative scalar curvature, right? But if its ADM mass is negative, right? Then one can do some conformal changes for the metric G, and conform changing G to get a metric G bar, right? It is still AF, asymptotically flat, and non-negative scalar curvature. And actually, scalar curvature is strictly positive somewhere. And and also you need to do some truncation for the conformal factor, so that this G is actually flat. It's flat metric, all set of a larger compact set, right? And then we can cut off the manifold, right? On the part this metric G bar is flat. Then you can we can cut that by using cube, right? And then glue the opposite set to get a torus. So basically, this compactification or on this assumption, or get a positive scalar curvature metric on torus collect sum with some compact manifold M1. And here M1 basically is the one-part compactification of the AF manifold M. Right? So this this will lead to a contradiction to Geroch conjecture. So basically, this kind of compactification argument can reduce the positive mass theorem, the proof of positive mass theorem, to the Geroch conjecture, right? So now, so Geroch conjecture is is about the existence problem of positive mass theorem, about positive scalar curvature metric. Right? So I think the most classical one should be for the torus, and then for the like sum of torus with a closed manifold, the M1. Right? And for this compact case, so first proved by Shenyao, still use the minimal surface method, and then Gromov loss in the Geroch operator method. So now, actually, then more recently, people also so want to study the so-called positive mass theorem with arbitrary end, right? That is for manifold with multiple ends. Probably one of them is AFN, and the other ends may not AF, right? Could be like a cylindrical or some other types, right? So then if we still do the Shenyang low cap compactation for this in this case, then people will need to study the so-called generalized Geroch conjecture, right? So positive mass theorem with arbitrary end will reduce to the generalized Geroch conjecture. In this case, the manifold this M1 would be non-compact, right? And but here we still require the manifold to be complete, now the metric to be complete. So this for this generalized Geroch conjecture, for dimension between 3 and 7 was proved by tradition and Lihe. Right? So it's pretty recent work actually. And in spin case, this was proved by Xianzhe Wang and Weiping Zhang. And also in dimension 3, it also was proved by the Soda, Eng, and Yang. Right? So this is yeah, the rough history for the study of Geroch conjecture, right? And also its generalization. Okay, so now all these are about smooth metrics, right? So then now we are interested in singular metrics. There are many motivations here. Just to list some of them. In Gromov's polyhedron comparison program, I need to consider the existing problem of singular metrics on torus, or like a convergence problem on the curvature bonds, scalar curvature bonds, right? The limited spaces may have singularities, and also like other stability problem of positive mass theorem, and so on. Right. Okay. So but let's look at an example, right? It's a negative mass structure. Okay, so this is very similar as the Euclidean structured metric, but here we just look at the three-dimensional case now. So this is still a conformal deformation of the Euclidean metric, right? We still use the brace function of Laplace operator, but this time its sign becomes negative, right, instead of a plus in the Euclidean structural metric. So then this metric only defined for on the domain is R greater than 2m, right? And we still have this is still scalar flat, right? But this time the mass will be negative, right? So negative m. Okay, then near R equal to 2m, one can rewrite as a metric in this way by doing a change of variable. This can be found in some previous papers, like Shi and Tan or other people's paper. Yeah. Okay, so you can see if we look at the metric in this way, then it's first two term the main term, and the third term is a higher order term, right? So, error term. So so from this first two terms, we say that this metric has a singularity for sigma equal to 0, right? So sigma equal to 0 corresponds to R equal to 2m. So we say for this kind of singular metric, the positive mass theorem doesn't hold. And actually, this is example for more generally what we call the Hall singularity, right? So the model of the RB Hall singularity this is a product manifold is integral times closed smooth closed manifold, and the metric and the model metric is this kind of water product metric. Warping function are to base power, because RB Hall. And when b equal to 1 is just the model cone, right? It gives us conic singularity. That's the simplest case as discussed in Milan's talk. So it's just isolated conic singularity when b equal to 1. Okay, and for manifold with oscillated RB Hall singularity means near a singular point, the metric is a perturbation of this model singular metric, right? With error term h decays at a certain rate, right? Okay, and we see for the example we saw in previous slides is I think, sorry, this is a negative mass structured metric is an example for the RB Hall singularity, right? For b equal to 3/2, and actually this is a critical number here, right? You'll see that in next slides, right? Okay, so we know for general Hall singularity, the Porter mass theorem doesn't hold, but we can show that in joint work with Professor Dai and Yukai, which is support mass theorem still holds for manifold for AF manifold with oscillated conic singularity, right? Here we still assume the dimension is between 3 or 7. For non-spin case, all manifold is spin, right? So and actually, yeah, in last talk, they already proved that the Porter mass theorem for AF manifold with more complicated singularities, right? But I think they are just for spin case, right? So right, we also have the rigidity part that says mass equal to 0, then the manifold is asymmetric to this the Euclidean space. So in this case, no singularity can appear, right? And although as a consequence of Hazlitt's supportive mass theorem for AF manifold with boundary, right? We can show that the Porter mass theorem still holds for general RB Hall singularity with b strictly greater than 1, right? And then we also need to assume the Yamabe constant is greater than 0. So Yamabe constant for the link for cross section, right? And in dimension 3, Miao by using Miao's mass to capacity inequality, he can obtain a positive mass theorem for with RB Hall singularity with b strictly greater than 3/2. So combine this with negative mass structured example, we see so this is a sharp result, right? So we can get in the dimension 3, and of course one can expect this kind of sharp result for general dimension, but for that probably people need to first prove mass to capacity inequality for high dimension. But I think so far it's still unknown. Okay, so then so as a smooth case in this conic singularity setting, we can also do compactification argument, right? Like Shenyang low cap compactification. Then the Porter mass theorem can be reduced to the existing problem of Porter scalar curvature. So conically oscillate. So conically singular Porter scalar curvature metric on torus collect sum with some compact manifold, and because and we can also prove the non-existence result for this kind of singular metric or torus collect sum with a closed manifold. And we also have a rigidity result we say for such singular metric with a non-negative scalar curvature. This metric has to be flat and actually smooth. Right? So in the statement of theorem, we assume M. We say M is a closed manifold, right? It's a closed compact manifold. But actually, the only metric has a singularity. But actually, we can also deal with the topological singularity. And here are some earlier work. This also Chow even dimension for error-ineligible manifold. Right? It can get a non-existence of Porter scalar curvature metric with oscillating conic singularity, and also Shi for they obtained the non-existence result for Porter scalar curvature metric with oscillated conic singularity on torus. Okay, so now let's very briefly look at the proof of Porter mass theorem. So so main thing here to do is okay, so this is just for the this first part is for non-negativity of the mass, right? So for this part, we just need to do a conform change for metric G, right? This so this kind of technique actually dates back to Schoen's resolution of Yamabe problem, and it turns out to be very useful. Although in our second part, in the second part of talk, we'll also use this kind of conformal blow-up technique to deal with singular metrics. So the conform factor will be a harmonic function, harmonic function with certain asymptotic behavior and infinity, and also near conic singularity. And then after we saw this harmonic function, then we do a deformation for the harmonic function, and use this deformation deformed function U delta to conformally change the metric G. Right? And then relationship between the mass of G delta and G is here. So then basically, after we do this kind of let me draw a picture. So this is conic singularity, right? After we do this, this is G, and after we do this conformal changing, basically we changes conic singularity to a conic end. So we get a complete metric. We can use the Porter mass theorem with an arbitrary end, or just a cut off the manifold along a link to get to get a AF manifold boundary, and use the Porter mass theorem with boundary to get the non-negativity of mass of G delta, right? And then in that G goes to 0, get the non-negativity of the metric G, right? This is a basic idea for the proof of non-negativity of the mass, right? So here the key thing is to solve this this harmonic function, right? So do some analysis. I will not talk about detail of that. Okay, so and then for the rigidity part, right? So we start with so now we assume mass is 0 and the scalar curve is non-negative. From this and combine the non-negativity of the mass for the non-negative scalar curve metric, we can show the Ricci flatness of metric G, right? And also you can get the link. The Ricci curvature of the link of the cone has to be a -2, and then we can solve. We can find some harmonic functions yi, because asymptotically harmonic correlate, because it's asymptotic to is asymptotic to some Euclidean correlated system on AF end, and near the conic singularity, it has this kind of a partial asymptotic expansion. Yeah, so here lambda 1 is the first non-zero eigenvalue of the Laplace on the cross section, and phi I is the eigenfunction. So then one can use the literature estimate for the first eigenvalue of the function of the Laplace acting on function. One get the lambda 1 has to be greater or equal to n minus 1, and then by the Berkeley formula, one can express the mass, the Indian mass, in terms of its yi, actually the integral Hessian of yi, and then from the assumption mass is 0, we get the dyi apparatus. So then from this one can get the lambda 1 has to be a minus 1. So then use Obata's rigidity result, we see the cross section of the link must be a standard sphere. So this will in this case, then the metric G will have W1n equiregularity, and then for this kind of matrix, the rigidity result has been obtained by Jiang Shenzhang. Right. So here in zero work, actually, they also use RCD, the theory of RCD space. Actually, use the rigidity part for the volume comparison for the RCD space. Right. So this is the first, I think the first part of the talk about the conic singularity. Okay. So now we'll move to the more general L infinity matrix or uniform Euclidean matrix. So before that, let's look and recall a classic result about existence problem for positive scalar curvature metric. Right. So and the Yamabe invariant. Right. So here for closed manifold M, let's recall the Yamabe invariant. It's also called the Schoen. Yamabe constant, also Schoen constant or sigma constant, is defined in this way. So first we take the infima for the total scalar curvature in a conformal class, and then take the take a soup for this Ym. Take soup over all conformal classes. Right? Then get sigma m. This will be diffeomorphism invariant of the closed manifold M. Right? And this constant will give a very nice characterization for the existence of a positive scalar curvature matrix. So this is a classical result of Changliang Wang and Schoen that says for closed manifold M, M admits a smooth positive scalar curvature metric if and only if this Yamabe invariant is so Yamabe constant is greater than or equal to 0. It's strictly greater than 0. Okay, and the rigidity part says that if the manifold has a non-positive Yamabe constant, then any non-negative scalar curvature metric must be Ricci flat. Right? Must be Ricci flat. So combine this and the solution of Geroch conjecture, we see the torus. The Yamabe constant of torus is 0, and the Yamabe constant of torus collect sum with closed manifold is if closed spin manifold M must be non-positive. Must be non-positive. Okay, so this is about the smooth matrix with positive scalar curvature or non-negative scalar curvature, right? So now for so then the natural question would be how about the singular matrix with positive scalar curvature or non-negative scalar curvature, right? So kind of the generalization of this result to a singular setting. For that, there's a conjecture by Schoen. Yeah, this conjecture says if we have a closed manifold, right, with a non-positive Yamabe constant, right, then now consider the so-called L infinity or uniformly Euclidean metric that is a measurable symmetric two tensors finished here, such that this two tensor can be bounded from both below and above by a smooth metric. Okay, for such L infinity metric, right? If it's a singular set, not too large in the sense of its codimension is greater than equal to 3. Then any this kind of L infinity metric, it has a non-negative scalar curvature on the smooth part, can be extended smoothly to the whole manifold. It must be Ricci flat. This is a conjecture, right? So now so in this conjecture, so the codimension of singular set is assumed to be greater than equal to 3. And in the case of a codimension of singular set equal to 1, that means you already in general says the codimension of the Hopper surface or something like that. So this was studied, and some conditions should be imposed on the mean curvature of the singular set. And in the case of codimension 2, right, this was studied more recently by Changliang and Metallidis. In this case, we still need some geometric assumptions. Cone angle must be less than equal to 2 pi, and for the cone angle strictly greater than 2 pi, they give some counterexample. But so here in this insurance conjecture, he thought if codimension of singular set is greater or equal to 3, there are no any other geometric condition should need here, right? But okay, so and I think this probably this Schoen conjecture can be viewed as a converse of codimension 3 surgery for positive scalar curvature metric. So that's obtained by Gromov-Lawson and Xianzhe Dai independent. Okay, so there are many interesting progress on this Schoen conjecture. Actually, the all recently, right? Recent progress. So I think the first kind of progress is about the Ricci flatness of matrix on its smooth part. So for example, for the four-dimensional enlargeable manifold, that's obtained by Cazares, and in the case of a spin manifold with some with fundamental group satisfies certain condition, and also oscillated singularity cases was obtained by Changliang Frank Zayden. And Wang and Xie also studied this problem on torus manifold admitting a ellipse map to a torus with another degree. And for the non-isolated singularity case, in this case, you need to assume the codimension of singular set is greater than or equal to half of n plus 1. Right? This condition coming from the blow up argument, right? So this restriction for the codimension guarantees the completeness of the blow up metric, right? And Shi Wang Wu Zhu, they studied Shenyang shake manifold and obtained the Ricci flatness on this manifold. And for the smooth extension part, so the first result is obtained by Changliang and Metallidis. Yeah, they proved the Schoen conjecture in dimension 3. Right? So for L infinity metric, and so the Chengli and Tan proved the smooth extension, get a smooth extension result for continuous metrics, continuous metric based on Ricci flow method. And a very interesting counterexample was given by counterexample to Schoen's conjecture given by Xianzhe Frank Zidane. Right? They construct some positive scalar curvature matrix with isolated conic singularity on simply collected manifold with the permanent dimension only need to be greater than equal to 5, right? But in order to get conic example, this manifold cannot admit a smooth matrix with positive scalar curvature, right? But for that problem, we need some restriction on the further restriction on the dimensions, right? But they do get some counterexamples. So that means we cannot hold the Schoen conjecture holds in general, right? But we can still confirm the Schoen's conjecture for manifold have enough topology, like on the torus collect sum with a closed manifold, right? For this kind of manifold, right? We get a smooth extension result for non-negative scalar curvature L infinity metric. Right? So now here we need to assume codimension is greater than equal to 4, and also half of n plus 1, right? For this restriction on the codimension, I already mentioned the basic reason, and we need a codimension of singular set greater than equal to 4 because we'll need to use the theory of RCD space for that. For in order to check the RCD condition, we need to assume the codimension is greater than equal to 4. Right? I will talk about that in next few pages. Okay, so so in particular, we can confirm the Schoen's conjecture for oscillated singularity for this kind of manifold, right? Okay, so this is our main result in the second part of the talk. Okay, and as I mentioned here, the very important thing, a very important ingredient in our proof of this theorem is this result about the RCD condition, right? We can basically show that we check the RCD condition for L infinity metric if the singular set of the L infinity metric is greater than or equal to 4, and also Ricci curvature has a lower bound on the smooth part, right? On the smooth part, and this kind of result has been obtained for the stratified space. I think that is a space discussed in Milan's talk. Right? So, and also for so-called almost smooth compact metric mirror space. But there is in Honda's work, this condition is assumed, right? So U is a eigenfunction of Laplace, right? He need to assume the the gradient of Laplace, the gradient of eigenfunction of Laplace must be L infinity. But here, so basically after we have this gradient estimate, then we can use the same method as Honda, and also this for this working for stratified space show the we can check the RCD condition for L infinity metric. So the main thing will be this kind of gradient estimate, right? So let's let's quickly recall the definition of RCD space, right? So basically, it's okay. So the RCD space has some different but equivalent definitions, right? So here we use this one. This this is more suitable for our purpose here, right? So main thing will be weak Bochner inequality, right? So basically, change the Bochner formula to this kind of weak Bochner inequality. Yeah. So for in our setting, so first three conditions can be checked relatively easier, right? So the main thing will be check this weak Bochner inequality. For that, we can do that first for the eigenfunctions of Laplace operator, and then for the finite linear combination of eigenfunctions of Laplace operator, and then take limit to get to check this inequality for all manifold for all functions, right? For all test functions. Okay. Right, this is a main idea. So so for the gradient estimate of the eigenfunction, so the main thing will be this gradient estimate of eigenfunction. This is why we need this codimension greater than equal to 4. Okay, so you have to get this gradient estimate of the eigenfunction. We do that in 2 steps. So the first step, so we first get a very rough gradient estimate, right? We're using Digital-Nash and Morse estimate, and also Zheng Yao's gradient estimate. Right? Since here we have Ricci lower bound on the smooth part, right? You can use that. And but this estimate is pretty rough because here you can see we already know the R is the alpha. This index is between 0 and 1. So this will so this part is still can go to infinity, right? As Rx goes to 0, right? That means when we approach to the singular set, this will blow up. Then the second step will basically need to assume the codimension, right, of the singular set is greater than equal to 4, and then use the Bochner formula. We can get the L2 estimate for the hash of U, and then use Cartesian inequality, get differential inequality for the norm of gradient of eigenfunction, so in barrier sense, and then use the Morse iteration argument to get an L infinity estimate of gradient of U. And this actually, the second step is idea is similar as Modena estimate on the for the stratified space. Okay. So so after we get this gradient estimate, then we can basically check the RCD condition for L infinity metric. Okay, now let's look at the sketch of the proof of the smooth extension result. Okay, so still the first step is to show the non-existence of positive scalar curvature L infinity metric on this kind of manifold. This basic idea is still conformal blow up, right? We can do a conformal change for the metric by using the Green's function of conformal Laplacian with but here we need to in the conformal Laplace we have to do some truncation for the scalar curvature, right? Since scalar curvature goes to infinity, right? Near the singular set, right? Okay, so but anyway, we under this assumption for the codimension, we can after we do the conformal blow-up, we can get a complete, we can get a complete metric, complete metric, and then we can use the generalized Geroch conjecture, the resolution of general Geroch conjecture of Changliang and Lihe and also Wang and Zhang to get the non-existence of positive scalar curvature L infinity metric on this manifold. So then we'll see for any L infinity metric with non-negative scalar curvature on this manifold, right? This metric must be Ricci flat on the smooth part, right? From the first step, we get Ricci flattening on the smooth part. So then by using our result for the RCD condition of infinity metric, we know its manifold has to be RCD 0n, right? So n is the dimension. Okay. So then we can use Mondino and Weiss topology reduce result of the RCD space, right? Since now we have enough fundamental group to conclude the rigidity. And for the oscillated singularity, actually, we can also use Smith and Young's remote singularity result for the X-time metric to get a stronger small-scale tension result, actually, right? Okay, so this is the main idea of the proof of small-scale tension result. Okay.
So, Changliang, so I have a question. Actually,
okay.
So
Mhm.
so you first prove this space is RCD and then use it to prove something. I think I'm a little bit lost.
Yeah. So okay. You mean how to prove that's RCD space? Or
No. After you
oh,
prove
after
that,
this,
it
right?
means kind of why do you prove it's RCD? Same that you are going to use it for some other stuff, but I haven't understand it.
Oh, okay,
Yeah.
okay. So right. Let's say, let's don't talk about RCD. Let's say just if we have a smooth Riemannian manifold, right? If this let's say uh uh if this is Ricci curvature is non-negative, right? And its fundamental group is the same as that of torus, right? Then this will be it's just it will be just it can only be the torus or cover
Yeah, I
of
know.
the torus, right?
Yeah.
Basically use this kind of thing. Right.
Okay.
This was generalized. This kind of result was generalized to the RCD space by Mondino and Wei. Right.
Okay, they extended it to RCD space.
Yes. Right. Yeah. Yeah.
Oh, okay. I got it.
Yeah. So here we have we already have a torus on the manifold. This is fundamental group will be right. Okay.
Yeah.
And this the torus. Yeah, so we can
Yeah.
use this too. Yeah, but here
Oh,
for this,
yeah.
okay, for this case of a general case, this small scale tension is just up to that just means that's isometric to a smooth Riemannian metric as a metric space, right? But for the oscillated singularity, we can kind of do a sort of a real the small scale tension of the metric, right? But up to some change of uh, uh, diffeomorphism structure. Right? I mean differential structure. Right? Yeah. Okay. Right. So this is a sketch of the proof. Okay. So and think the finally I would like to mention. Okay. So since main theorem we already stated that for the spectrum manifolds torus collection with closed manifold, but for the enlargeable manifold, we can also get smooth tension for the oscillated singularities, right? So here the RCD space is also very theory of RCD space is still very crucial. Yeah, since in this case Chishin Frank Zayton or they already proved the Ricci flatness of the metric G on the smooth part. And then is our result for the RCD space. We can see this this meant for the RCD space. Okay. And then this time we use the splitting theorem for RCD space. It's also generalized from the small setting to the RCD space. This is for this is done by Gillies. Yeah. So and then we can just adopt Gromov-Lawson's proof for in smooth setting for this kind of result for the rigidity result on the for rigidity result for non-negative scalar metric on enlargeable manifold. Since in their result basically just use the kind of distance with a metric structure. Right. So after we get this kind of splitting by using after we get this RCD condition and by using splitting theorem, we can still adopt their result to this setting. Okay, I think, yeah, I'll stop here. Thank you for attention.
So any questions?
May I just ask about why is the codimension greater than or equal to 4? Just have not followed it.
Oh, okay. That's because here, yeah, you ought to get this estimate actually for the grade. Yeah, it's grade estimate. We have to assume this is codimension is greater than equal to 4.
Okay,
Yeah.
thank you.
I think for so it's actually more precisely for getting this estimate for hashing, right? Hashing view.
Oh, okay. So it's used in the hashing estimate.
Yes, yeah. I think in hashing estimate we already needed this assumption. Yeah, but probably this just should be a technical assumption, I think. Yeah.
Another question is about the last step from Ricci flat to flat. What is the condition of the singular set for you to deduce the flatness from the Ricci flat?
You mean this proof?
The last step.
Here.
Yeah. So here S can be an arbitrary singular set
No,
of.
sorry. Just for yeah, I should emphasize this is isolated singularity. Isolated singularity. Yeah.
Oh, so isolated is essential
Just the
in
point. Yeah, just a point singularity. Yeah. It's yeah. Yeah. Singular set are just some points, right? Consists of some isolated points.
So it is used in the application of the gauge splitting theorem written here.
Oh no, not for this. This splitting theorem holds for general RCD space. Yeah. For RCD space, general RCD space. And it can be very general. Right? It's much more general than the setting we consider here. So our space is just mean and most part is I mean almost is a manifold, right? Just some singular point, right?
So what is isolated used in this last step?
I think in this part they already used so this oscillated singularity condition, I think. Yeah. Yeah.
Okay. Thank you very much.
Okay. Yeah, if I remember, yeah, correct.
So any more questions? Okay. So I have another question is, so your main goal or your group main goal is try to understand the Schoen's conjecture, right?
Yeah, right. For the second part, yes, right. Yeah.
Oh, okay.
Yeah.
So you said Cheney Franco then their result said the conjecture is wrong, right? For the singularity.
Yeah, in general, it's cannot be true, right? So they give some very nice counterexample, actually, right?
Oh, okay.
But they already
their manifold is spin or non-spin. I have a question. The spin, right?
No, could be spin or non-spin.
Spin manifold. Okay.
Oh no. I mean both for both. It's an example, right? For both.
Oh, okay.
Yeah, they don't have spin
Construct.
Yeah.
Oh, simply connected with. Oh, okay.
Yeah.
Okay.
But yeah, in the same paper, they already give some positive answer, right? So some topology.
Oh, in some cases, right?
In the same paper, yeah, they give some counterexample and also some positive answer to the conjecture, right? But topology, is positive. Awesome.
Oh, the same paper. Okay, you said the
Yeah,
same paper.
the same
I'll
paper,
take
the same
example.
paper. Yeah. Right.
Okay, I got it. Okay, thank you. So,
Yeah.
so any
thanks.
other question? Okay, so no, since there is no more question, let's thank Professor Wang again.
Okay. Yeah. Thank you. Thanks. Thank you.